Hello all, today I am going to see the first year BSc third unit in physics, that is relativistic mechanics. Okay, coming to the introduction, I am Vijayawada-1 working as a physics lecturer in Department of Physics at K.B.N Degree College. Okay, let us go into the table of contents. In this session we are going to see about the introduction to relativity, reference frames, and what the special theory of relativity tells us and the postulates regarding the special theory of relativity. And then we are going to see the Michelson-Morley experiment and then the significance of Michelson-Morley experiment, and then we are going to see the null shift and then length contraction and then time dilation. Okay, without wasting much time, let us go into the contents. Now, first one is introduction of relativity. Now, what does the relativity mean? The way that anything except light, okay, the way that anything except light moves through time and space only depends on the position and movement of someone who is watching it. Okay, it totally depends on the movement of someone who is watching it. That is what the relativity means. Okay, now in the relativity we are going to see that length is relative, position is relative, size is relative, time is relative, and we can say motion is also relative. Now I will go say you that the examples of how the length is relative, position, size, time, and motion and all. Okay, now first I am going to say about the length is relative. Okay, once Akbar drew a line on the floor to his coat and asked the wise men to shorten the line without rubbing it. He asked the wise men to shorten the line without rubbing it. Everyone was puzzled that how is it possible to shorten a line without rubbing it or doing any alterations to it. Then at the same time, Birbal came forward and drew another long line near the previous line. Okay, Birbal came and drew another line beside the previous one. He then asked the king, "Sir, which of the two lines is shorter?" The king said that the line drawn by me is shorter than the line drawn by you. Birbal smiled and said, "My lord, so the line drawn by you has been shortened without rubbing it." Yes, the line drawn by him is shortened without rubbing or doing any alternation to it. This is what the length contraction means, that the length is relative. A line at the same time may be shorter or relative to while another relative to each other. Okay, this is what the length is relative means. Now coming to the position is relative. Suppose if you assume a river bank, a bank, okay, two persons are standing besides and seeing each other on the banks of the river. Okay, two persons are watching each other on the bank of the rivers. Then there exists a house on the bank of the river. A house exists at the bank of the river. Then the person one says that the house is to the left of me, and the person two says that the house is right of me. Okay, one of the person said that the house is left to me and the other person said that the house is right to me. Then which of the two options is right? Yes, both the options are right. Why? Because to one person the house is in the left side and for the other person the house is on the right side. So both the options are right. From this example we can say that the position is also relative. Okay, from this example we can say that position is also relative. Now coming to the size is relative. If you consider a rubber ball and a hockey ball, okay, if you consider a rubber ball or a hockey ball, okay, the size of atom is smaller compared to the hockey ball, right? Largely smaller compared to the hockey ball. If you consider the same hockey ball with the size of the earth, it is nearly smaller than the earth, as we can say. Okay, that is the hockey ball is extremely smaller than the earth. Now we can say that the size is also relative. Now coming to the time is relative. If I ask a person what's the time now? He says that we can accept an answer that in India, the time in India is different from the time in America and different for the other place in the earth. Okay, from this example we can say that the time is also relative. Then coming to the motion, if you consider a train moving with a 60 km/h speed, if you consider a train moving with a 60 km/h, now we are going to see the perceptions of three persons, three observers. The one who is watching from the earth, and the other one who is traveling along with the train with a 20 km/h, and the third person is watching the train in the forward direction, and he is moving with 30 km/h. Okay, here I said three persons. The one is watching from the earth, the other one is moving along beside the train with the 20 km/h, and the other one is watching the train which is coming towards him with a 60 km/h, and the third person is moving with 30 km/h in the opposite directions. Okay, from the first person we can say that the train is moving with 60 km/h. Why? Because he is at rest and he is watching the train. As the train speed is 60 km/h, so that the train moves with 60 km/h. Now with respect to the second person assumption, we can say that the train is moving with only 40 km/h. Why? Because as the train moves, the person who besides the train also moves with a 20 km/h speed. Okay, so in his perspective he will see the train moving with only 40 km/h. Okay, now coming to the third person, as he is moving with 30 km/h speed in the opposite direction of the moving train, he will observe the train is moving with 90 km/h. Okay, now coming to this motion is relative, how we can say is, the first person said that the train is moving with 60 km/h. Why? Because he is at rest. Now second person said that the train is moving with only 40 km/h. Why? Because that person also moving with 20 km/h speed beside the train along the same direction. Now the third person said that the train is moving with 90 km/h. Why? Because the train moves in the opposite direction with respect to the third person. Okay, now the theory which deals with the relativity of motion and rest, the theory which deals with the relativity of motion and rest is called theory of relativity. Okay, the theory which deals with the position of motion and rest is called theory of relativity. Okay, the theory of relativity is divided into two parts. The first one is special theory of relativity, and the second one is general theory of relativity. Okay, now we are going to see what is special theory of relativity and what is general theory of relativity. Okay, special theory of relativity. The special theory of relativity deals with objects and systems which are either moving at a constant speed with respect to one another or at rest. Okay, the special theory of relativity deals with the objects and systems which are either moving at constant speed with respect to one another or at rest. Here we can see the example below the special theory of relativity. The picture determines the example of special theory of relativity. Now moving to the second one, general theory of relativity. The general theory of relativity deals with object or systems which are speeding up or slowing down with respect to one another. Okay, it deals with object or systems which are speeding up or slowing down with respect to one another. This is what the general theory of relativity determines us. Now moving into the second topic in today's session, it is about the reference frames. Okay, the frame of reference, we can say reference frame or frame of reference. The motion of a body has no meaning unless it is described with respect to some well-defined coordinate system. Okay, a body has no meaning unless it is described with respect to some well-defined coordinate system. Okay, even if you want to plot a point, plot a graph, you need coordinates xy axis. Without that we can't keep a point. Okay, you need xy axis. In the same way, the motion of body has no meaning unless it is described with respect to some well defined coordinate system. That coordinate system is called as frame of reference. That coordinate system is called frame of reference. Thus any system relative to which the motion of an object can be described is called a frame of reference. Is called a frame of reference. Okay, is called a frame of reference. Okay, now we are going to see the types of frames of reference. Okay, there are two types of frames of reference. They are inertial or unaccelerated frames, and the second one is the non-inertial or accelerated frames. Okay, there are two types of frames of reference. They are inertial and non-inertial frames. Okay, now coming to the inertial frames. In inertial frames, a body not acted upon by an external force is at rest or moves with a constant velocities. Or in simple words, we can say that a body or the inertial frames which obeys the Newtonian laws or Newtonian mechanics or Newton's laws is called as the inertial frames. Or we can say a body not acted upon by an external force is at rest or moves with a constant velocity. Okay, the important point in inertial frames is if a body is moving with the same velocity as the inertial frame, then we can say that the body is at rest. Okay, the inertial frames are also called as unaccelerated frames. Okay, unaccelerated frames, and these frames will obey the Newton's laws. Okay, now coming to the non-inertial frames, a frame of reference is said to be non-inertial frame when a body not acted upon by any external force is accelerated. Okay, these are also called as accelerated frames. Okay, in this frame the Newton's laws are not valid. Okay, in inertial frames the Newton's laws are valid. In non-inertial frames the Newton's laws are not valid. Okay, below you can see that what is inertial frame and what is non-inertial frames. Okay, now we are going to see the third content, the special theory of relativity postulates. Okay, the postulates of special theory of relativity says that upon examining a large number of problems of the detection of either wind and the experiments which had been performed to save the either wind theory in 1905, Albert Einstein drew two important conclusions. Okay, the two important conclusions, these are known as the postulates of special theory of relativity. He came up with two very important conclusions. Okay, they are the pillars on which this theory is based on. The postulates are, the first postulate is the fundamental laws of physics are the same when stated in terms of two frames of reference in uniform translatory motion relative to each other. The fundamental laws of physics are the same when stated in terms of two frames of reference in uniform translatory motion relative to each other. Thus follows from the fact that there is no universal frame of reference. Thus we can say that there is no universal frame of reference. Okay, this is what the first postulate says. Now coming to the second postulate, the velocity of light in free space has the same value for all the observers, irrespective of their state of motion of the source and observer. No signal can be transmitted with a velocity greater than that of light. Okay, the velocity of light in free space has the same value for all observers, irrespective of their state of motion of the source and observer. Okay, this is what the second postulate determines. Okay, now going into the fourth content, Michelson-Morley experiment. Okay, the Michelson-Morley experiment designed to measure small changes in the speed of light and was performed by Albert A. Michelson and Edward Morley. This experiment was performed by Michelson and Edward Morley. They used an optical instrument called as interferometer that Michelson invented. Okay, Michelson invented an interferometer. They used this optical instrument in this experiment. This device was used to detect the presence of ether. Okay, this device was used to detect the presence of ether. The outcome of the experiment was negative. Yes, the outcome of this experiment was negative, thus contradicting the ether hypothesis. This will be contradicting the ether hypothesis. The failure initiated research which led to the proposal of theory of relativity. This failure is led to the theory of relativity, this Michelson-Morley experiment. Now coming to the Michelson interferometer, this is how it looks like. It consists of a light source, two mirrors and ether current. Okay, this is how the instrument looks like. Now coming to the significance of Michelson-Morley experiments. The null result of experiment lead to the total rejection of either hypothesis. The null result of experiment lead to the total rejection of either hypothesis. The second significance is the null result suggested that the speed of light in vacuum is the same in all frames of reference which are in uniform relative motion. Okay, these are the two significance from which we can conclude from the Michelson-Morley experiment. Okay, now coming to the fifth one, it is null shift. Okay, Michelson, what null shift says is Michelson and Morley expected change in fringe shift. They expected a change in fringe shift was less than the half a fringe, but they observed a shift of about 0.01 fringe. Okay, they expected a fringe less than half a fringe, but they observed a shift of about 0.01 of fringe. Of course, this shift is within the limits of the error of observations. That is a small error. The shift is within the limits of the error of observations. They repeated the experiment at different points on the surface and at different seasons of the year, but they could not detect any measurable shift. So it was a null or negative shift. So they concluded that it was a null or negative shift. This is what the null shift says to us from the Michelson-Morley experiment. Now coming to the sixth content of this today's session, it is length contraction. Okay, it is length contraction. The length contraction is defined by a rod of length L traveling with a very high velocity in a direction parallel to its length appears shorter to a stationary observer. Okay, I repeat, a rod of length L traveling with a very high velocity in a direction parallel to its length appears shorter to a stationary observer. This is what the length contraction is. Okay, length contraction is given by the relation L is equal to L naught square root of 1 minus V square by C square. Okay, where L is the length where observer is moving relative to the length being measured. Okay, and the L naught is the length where our observer is at rest relative to the length being measured. Okay, it is given by L is equal to L naught square root of 1 minus V square by C square. Okay, now coming to the last content of today's session is time dilation. Okay, apparent lengthening of time in the moving frame for an observer in the stationary frame is called time dilation. I repeat, apparent lengthening of time in moving frame. In the moving frame, apparent lengthening for an observer is in the stationary frame. This is what the time dilation is. It is given by the relation delta t dash is equal to delta t naught by square root of 1 minus V square by C square. Okay, where delta t is time where clock is moving relative to the observer. The second one is time where clock is at rest relative to the observer, or we can say the proper time. Delta is nothing but the change. Okay, where V square is the velocity and C is the velocity of light. Okay, this is the expression from the this is what we concluded from the time dilation. Okay, Thank you for listening.